Next, we will discuss about the process of electrolysis, or we call the cells as electrolytic cells. So for these type of cells, we still have, of course, the anode and the cathode, so we have two different electrodes. The main characteristic for electrolysis process is that we connect them to a power source. So this power source will give energy to the system, so non-spontaneous reaction would be able to occur. We can have several different examples of the electrolytes for electrolysis. They could be, for instance, containing water like this. Other options would be molten salts. This is different with aqueous salts or the salt solution. For instance, say we have a simple salt that is NaCl. The first thing that we have to know in electrolysis is, of course, their ability to become a reduced form or to become oxidized. So the first step is always to identify the species that we have in the system. If we have the molten NaCl, so first case we have NaCl liquid, so this is molten NaCl. We only have Na plus and then Cl minus. Of course, Na plus in this case cannot release more electrons because Na plus is already the most stable form. So Na plus will instead accept the electrons and then it will become Na neutral or Na solid in this case. So you can form Na solid from the solution of Na plus. On the other hand, the Cl minus will have the tendency to form the gas, which is Cl2. So in this case, you have to balance this reaction by adding 2 electrons to the product side. The first reaction is reduction reaction. So this would occur at the cathode. As usual, cathode is a place for reduction. And the reaction at the bottom will occur at the anode because this is an oxidation reaction, just based on the position of the electron. So from here we can expect that we will have solid Na form at the cathode and Cl2, in this case normally gas. Cl2 gas will be formed at the anode. However, what if the water is present in the system? That means we have NaCl aqueous. In the system we have Na plus, Cl minus, but also H2O. Now H2O can also be oxidized and can also be reduced. You have to find the reaction for water oxidation and water reduction. So in this case, you have 2 competing species at the cathode and 2 competing species at the anode. So if we write down here, at the anode, we can have the oxidation of either the Cl minus or the oxidation of H2O. And similarly, at the cathode, we can have the reduction of Na plus or reduction of the H2O. So how do we decide which will happen? Of course, the parameter that we can use is the E0 reduction. For E0 reduction, the larger it is, the higher its tendency to undergo reduction. Therefore, for cathode, we will look for the one with the bigger reduction potential. This one will undergo the reduction reaction at the cathode. On the other hand, for the anode, we have to find the one that has the lowest potential reduction. That means it has the higher tendency to become oxidized instead. So in this case, normally we would have competing reactions and competing species like this. So first we have to determine which reaction that would occur at the cathode and at the anode based on the E0 reduction values. So please pay attention, especially when you have aqueous phase like this. That means you have H2O in the system that would be readily competing with both the oxidation and the reduction. The final aspect that we will study is the quantitative aspect of the electrolysis. To understand this, let's take a look at this example of problem. An electrolysis cell that deposits gold from Au plus ions operates for 15 minutes at a current of 2.30 ampere. What mass of gold is deposited? If you want to try this on your own first, you can pause this video for a bit. There are 3 tips to solve this problem. First one is for you to write down the balance reaction first, involving, of course, the gold, the ion form, and the neutral elemental form. And then find the mole of the electron, and finally, you can find the mass of the gold through simple stoichiometric calculation. Now let's take a look one by one. So first, the reaction would be Au plus electron, and then this will result in Au solid. Meaning that now we already have a balanced reaction. If you don't have a balanced reaction right away, of course you would have to balance them first. Now, because we already have a balanced reaction, we know that the mole of electron will be the same with the mole of Au, as in this case we have both coefficients being 1. Now, in the electrolytic process itself, mole of electron is equal to the current multiplied by T, or together they are the charge, divided by the Faraday constant, which is equal to 96,500 coulomb over mole. The T in this case has to be in second, and the current has to be in ampere. These are the units that you are going to use. And based on this data, you can solve it this way. The I was 2.30 multiplied by the time. The time was 15 minutes, but you have to convert it to second. So in this case, it will become 900 seconds divided by this number of Faraday's constant. You will get around 2.15 10 power to the minus second mole of electron. And since we have established that mole of electron is the same with mole of Au, therefore we can easily calculate mass of Au is going to be the same with mole of Au multiplied by the mm of Au, where the mole of Au itself is the same with mole of electron. So simply multiplying this by the mm of Au, which is 197, you can see this from the periodic table, you will get 4.20 gram of Au being deposited after 900 seconds at 2.30 ampere of current.